Right, so hi everyone. I'm Oren Duer, Principal Architect from Mellanox. And we would like to tell you about some of the things we're doing with SPDK in Mellanox around hardware offloads. We started investing in SPDK heavily in the last year or so. And we're actually using SPDK as a framework to deliver our customers a flexible way to use our offloads, to use our products. We'll be covering actually two kind of different aspects of the way we're using SPDK. One is in the framework of a SmartNIC, and we'll explain exactly what is a SmartNIC and how does it allow us to do NVMe emulation and how SPDK is used for that. And in a separate section, we'll discuss SPDK and the ability to do NVMe over Fabric Target offload with Mellanox Connectix NICs. And then some other ideas that we have for the future around other offloads. So let's start with a SmartNIC. What is a SmartNIC? A SmartNIC is a network interface with some CPUs inside it in a kind of a SoC, a system on chip. So you have a network interface, and you have the ability to run some software inside this network interface and do some stuff with the, obviously, network. So we see two interesting use cases for this. One is more for networking purposes, so you can run your OVS and some kind of network enforcements inside the SmartNIC. And so the host that is connected is using the SmartNIC can only have traffic running through specific rules. We're not going to talk about this now. And another exciting opportunity that SmartNIC allows us, and this is very interesting, we can actually emulate any kind of a PCI device towards the host. So when you take a SmartNIC from Mellanox, you put it in a server, you run a special software on that SmartNIC, on the ARM cores that are inside, and the host, instead of seeing a Mellanox network interface or Mellanox RDMA interface, can see whatever you programmed in the software. It can see, for instance, an NVMe device. And since it looks like an NVMe device that is locally attached on your PCI, it has PCI class of NVMe. It can have your vendor ID there, your device ID there. When the host sees that, it just loads the normal NVMe driver and starts working with it as an NVMe device, shooting IOs, admin commands, whatever. All those IOs, all these admin commands end up inside the SmartNIC in your software. And with this software, you can then choose what to do with each and every request. You can service it, you can send it to a network, wait for a response, do some manipulations with the request, maybe change the LBA addressing, maybe decide where to send it on the network. You can even change the data. You can encrypt it, decrypt it when it's coming back. So you're free to do whatever you want. This is the marketing slide on what's the big advantages of using it. I guess you can all agree that it's giving a lot of flexibility, a lot of options, like, for instance, serving bare metal servers in clouds. We see this demand growing a lot. So if you have a bare metal server and you still want to give NVMe volumes and you want the NVMe to come from a disaggregated storage server, then you can use this kind of technology. The host only sees the storage that you allow it to see from the SmartNIC, from your software that is running on the SmartNIC. And so on. You can provision, you can over-provision, you can do thin provisioning, you can do logical volume management, And of course, being OS agnostic, this is one of the biggest advantages here. If you do it well, it runs on Linux, on VMware, on Windows. For instance, Windows until now still don't have NVMe over Fabric stack. And I don't know if they are going to, but this solves the problem. You put a SmartNIC there. Windows has NVMe driver. Thank God for that. So you can work around that and still do some NVMe over Fabric traffic from within the SmartNIC. So this is the typical use case in a simplified slide. You have a host, and inside the host you have a SmartNIC attached to it, physically attached to it on a PCI slot. The host sees, when it's doing LSPCI, it sees an NVMe device. Therefore, it's loading the NVMe standard driver, inbox driver. And on top of it, you have application, file system, whatever you want. You're running your application. Now, application starts sending IOs to this NVMe device. Those IOs end up being serviced inside the SmartNIC using software running on the ARM cores in the SmartNIC. So what's the best framework to put inside the SmartNIC so that customers as you will be able to do something with these IOs? SPDK. So we put SPDK inside the SmartNIC, and we have like an SPDK emulation connector, I call it here. And this is the connector that gets the requests from the emulated device that the host is using. And from there, it's standard SPDK stack. So all those IOs are being submitted to VBDevs and the BDev layer. And from there, it can go out using any of the available SPDK BDev drivers. For instance, it could be the NVMF initiator, but not limited to. You can do the iSCSI, you can loop it back into the kernel and use whatever POSIX drivers you have in the Linux kernel running inside the SmartNIC. Anything you want, really. So what we explain customers is that using this, you have two options that you can use together or separately as you wish in order to achieve your goals. If your network protocol is one of the natively supported protocols with SPDK, for instance, let's say it's an NVMe over Fabric protocol, then you already have the network driver. You can put your secret sauce, your secret advantages that you want to put. You can put it as a VBDev. Therefore, you can see every IO request coming in. You have the chance to manipulate it, change it, redirect it, put it on this BDev, on another BDev, and send it down the stack. That's one place you can utilize. The second place is, let's say you have your own proprietary protocol, not NVMe over Fabric, some other, hopefully, RDMA protocol. In that case, you can just implement your own BDev driver, and there you go. I mean, you have SPDK, you know the APIs, you know how flexible it is, you know how it's tuned to be thread safe and lockless and memory management. Everything is already figured out in SPDK. You don't need our assistance for that. All we need to give you is this connector, and you're done from there. So this is how it looks like when you drill a bit down. So there are three things that such an emulation software needs to take care of. Three things that such a connector, an emulation connector, needs to take care of. Step one, the host is going to start by playing with some NVMe registers, setting the admin queue, physical address, the length, the completion queue, and so on, and then assert the enable bit, and then it expects the device to assert the ready bit. So work with registers. Second thing, you'll need to work with to respond to the admin commands, right? all the identify controller, identify namespace, and so on. And of course, the most important one, which is create IO queues. And the last one, you'll need to handle IO queues and all the traffic that comes from that. So these are the things we believe should be encapsulated in something like an NVMe emulation box with a lot of common code that takes care of registers, takes care of admin commands. But we believe that each hardware that will enable such a functionality will have its own way to communicate with the hardware in order to get these three things: the registers, the admin commands, and the IO commands. That's why I draw here like an emulation driver. So this is a vendor-specific driver. If you look at this box, it's kind of like a target. It has the essence of a target. Why? Because it has like a subsystem of this so-called target is actually an emulated disk presented to the host. It can be one of many. You can present one disk, you can present 10 disks, you can use SRIOV to present virtual functions of disks. Each and one of these disks is very similar to what we have today in NVMe over Fabric Target, a subsystem, right? You'll want to be able to create namespaces, just like you do for a target. You'll want to be able to bind a namespace to some kind of a backend BDEV, just like a target. But other things are irrelevant. For instance, you don't need to create ports and set a subsystem, assign it to a port and things like that. So it's something in between, but looks like a target. And of course, like the target, it generates reads and writes requests towards the BDEV layer. And then the common code would be the NVMe controller, right? So serving all the admin commands, serving all the registers, and parsing them and doing the right thing. So this is something we would like to do together and propose to the community to help us develop something like this and put all the right APIs in place. In general, things like register a new emulated drive and register a new emulated disk and get notifications for registers that the host has been changing and be able to change those back and so on. I listed a few of the conceived APIs that we might need. So we have this running actually in a demo just outside this door. And so far, without doing a lot of, performance improvements and optimizations, if we just terminate the traffic inside the SmartNIC with the SPDK null BDEV, we can see as many as 2 million IOPS being served to the host. It's very nice. If you take it further and drive them using the NVMe over Fabric initiator in SPDK, we can see 1 million IOPS. And again, this is just out of the box. We didn't yet, and we have a lot of ideas on how to optimize it, which is some other topics we would like to investigate together. I start here talking about the other SPDK offloads, unless you have questions about NVMe emulation. Yeah. 10 out of the 16 that we have. 16, we have on Bluefield, we have 16 ARM cores. So to see the numbers that I quoted there, we used 10 of those. Yeah. Okay, we'll have more opportunity in the end of the. Okay, now we have a lot of offloads that we would like to integrate into SPDK in our NICs and smart NICs. But for that, we'll need some kind of framework in which an application such as an NVMe over Fabric Target can interrogate and get internal information from the end devices or the devices along the way, so that such a feature can be used. So, for instance, in the example of offloading the target traffic directly to an NVMe disk, which is something we already showed last year. Today we have it already running in a demo. Sasha will show you the results. But to be able to do that, what we need is to be able to take the NVMe SQ and CQ that are the responsibility of the NVMe PCI driver in SPDK and give it to the NVMe over Fabric target application, because this application needs to communicate it into the NIC so that the NIC could just post requests directly to the drive. So how do we do that exactly? We have few ideas. We started talking with you, and Sasha will present more about that. So keep that in mind. While you're thinking about that, think about other kind of offloads that we're starting to look at. Our future NICs will support inline crypto, inline other things like logical volume management, RAIDs, things like that. And to be able to do that, we, as an NVMe over Fabric target application, will need to be able to get those configurations. Okay, so imagine that the NVMe over Fabric target was assigned with a namespace that happens to be a RAID 10 VBDev, and this RAID 10 VBDev is using 4 NVMe drives. At the end of the day, for the offload to work, the NVMe over Fabric target application needs to push all that information to the NIC, saying, these are the 4 drives you are going to work with. This is the RAID parameters, the stripe size, chunk size, and everything else. These are the SQs and CQs of each separate NVMe drive. Go ahead, and now everything is offloaded. You don't need the software anymore. Okay? Same thing about cryptology. If we would like inline encrypt, decrypt to be happening with the network interface, we need to somehow propagate the configurations that were done using this, the crypto VBDevs. We need to be able to propagate it into the NIC interface so that proper encrypt, decrypt could take place. So we don't have yet the answers, but this is just, to pitch and for everyone to, to start think about it. Okay, so now about NVMe over Fabric target, offloads, and the work that was done. And later, if you have more questions, feel free.
Thank you, Oren. Hi, my name is Sasha Kotchubievsky. I manage Mellanox group responsible for SPDK activities, a very small but growing group. And I'll update you about work that we do last half year and about our progress, and I show some results for SPDK over Fabric target offload. So I'll start with brief introduction to the technology. If you're looking to spec, you can find that local queues for local NVMe drives very close to concept of RDMA queues. So in a local NVMe drives, you just submit a request to receive queue and wait for completion by polling some queue in the memory. And it's the same true for RDMA. For RDMA, you submit send message and post CQ for completion. So if you in terms of data format, both standards very close. So NVMe over Fabric is just a capsule that adds some additional small amount of data to NVMe command. And completion, it's almost the same. So when we send completion over network, it's just a NVMe completion with a small amount of additional data. And if we have 2 well-defined standards, and from usage point of view, they are very close. So in both cases, we just submit work request to cycle buffer and polling for completion. What comes to mind is just to implement this process in a hardware. So let's look to this slide. This slide represents high-level diagram for SPDK NVMe Fabric Target, but it's same as for any kind of NVMe Fabric Target. So we have here network card, RDMA card, and NVMe driver on top of this card. And we have two hosts connected to this card. Each host open admin queue and a number of IO queues. So admin queues eventually establish association between host and controller. Once IO comes to the NIC, it comes through driver to NVMEF library. NVMEF library extracts data. It just takes buffers and depends on mode. It do RDMA read or write and push data to block device layer. And in block device layer, we have NVMe driver, and data comes through NVMe driver to local disk. Of course, having software layer for access to NVMe or Fabric Target and having a very nice abstraction of block device has great advantages. You can expose any kind of storage or NVMe or Fabric Target. But if we are talking about real NVMe drive, we can just take IO comes to the network card and put it into local NVMe drive without any CPU involvement. So this slide demonstrates how we can accelerate NVMe or Fabric Target by offloading protocol to the network card. So at the first, we should obtain hardware properties of NVMe driver, receive queue, send queue, doorbell, and bind RDMA QP with NVMe queues. Once we have this binding done, hardware will put IO directly to NVMe drive. So in this slide, we demonstrate that actually we use SPDK as a configuration and for control paths. We use it for configuration and for connection establishment. But in data paths, in actual data processing, we use only hardware paths. So target offload available in all our network cards starting from ConnectX 5. We have working code. We have demo outside this and it's available as a technical preview. This year, we're planning to submit all patches, all our work that is done in SPDK to upstream. And let's talk about changes in SPDK. So in this diagram, you can find high-level diagram of SPDK architecture. So I put here only relevant blocks. And so at first, we have a special API, user space API for configuration our hardware. So this API can be used in any kind of application, not only in SPDK. So this API and integration of this usage of this API in SPDK, we call it vendor-specific plugin. If we have a new interface, we should use it in RDMA transport, and we changed also NVMe Fabric Target library. And Unfortunately, we have to break nice block dev abstraction because we need access to underlying properties of NVMe drive, like queues and doorbell, and we did it. So more than we did some changes in core infrastructure of SPDK. Today, SPDK implements by default round-robin policy for spreading queues over available cores. If we have offloaded subsystem, so if we configured our subsystem as offloaded and we have capable device, we don't need. We can concentrate all QPs serving this subsystem on the same core. So here I'm talking about admin QPs, and we still have open IO QPs for commands that can be processed in our hardware. But if we are talking about future, we see that in a different way. We think that today RDMA functionality exists in SPDK in two different parts of SPDK, in NVMe Target and in initiator parts. We think that both parts should be merged in transport library, which allows us, the vendor provider, to extend this library in the same place. And so we're going to merge all RDMA core in the same place. So we're going to suggest that to community. We're going to implement vendor-specific plugin which will be responsible for NVMe Fabric Target offload and for future offloads that coming in next generation. So we're going to suggest merge of RDMA code in a single separate library, and with interfacing to vendor-specific plugins. And today this plugin will implement NVMe Fabric Target offload, but new more advanced offloads are coming. So for those offloads, we need access to internals of different virtual block devices, like crypto, RAID, logical volumes. So we suggest to create a general channel through and use this channel for communication between vendor-specific plugin in a network transport rail with block devices. Once we have it, so it will be very flexible. So it's happened. Okay, no problem. So it will be very flexible platform that will serve us and our other vendor providers for extending SPDK functionality. And now let's talk about performance result. So we did some benchmarking in our test setup. In this setup, we used Blue Whale Target. Blue Whale Target is a storage target which is built on top of a Bluefield chip, which includes ConnectX 5 network card and ARM cores. And we have initiator which runs on 868 platform. Both servers are connected with 100 gigabit network. We run RDMA read, RDMA write, 4K blocks, 16 queue depths. And we iterate over number of disks and see what is the CPU utilization we see in the case of software implementation and in case of hardware implementation. So let's look on this diagram. So vertical bars represent IOPS. You can see that IOPS are very similar. Even hardware offload overperforms software implementation. Standard SPDK target implemented in software. But very important is the lines. Lines represents core utilization. And In the case of software implementation, we need, in our platform, we need about 2 cores for serving one NVMe disk. And in case of hardware offload, we need only single core running SPDK for control paths, for connection establishment. So in both cases, actually, we can go to maximum throughput of our network. And in case of offload, we need just one single core for serving all possible data coming from one port of 100 gigabit network. And other cores are available for your applications. This slide represents the same result for RDMA write. So let me summarize. So we have, I think we have a great technology which allows to free CPUs for application use. We have, because both standards, NVMe and NVMe Fabric, well defined and very close from semantic point of view, the implementation very straightforward, very efficient, and runs very well on real hardware. Let me talk a little bit about our demo. So in our demo, we demonstrate both technologies working together. So we have Blue Whale appliance. We have Windows host with Bluefield adapter. In a Blue Whale appliance runs SPDK on single core, and Bluefield adapter in Windows host emulates NVMe local drives. So in our case, we run SPDK also on a Bluefield adapter for additional processing. And just for demo, we choose to add logical volumes. So SPDK, so data comes from host or PCI bus to Bluefield inside Bluefield adapter, and we utilize our hardware capability of snap technology, and we handle this data in application based on SPDK. And after that, data comes through RDMA network to remote target. In a remote target, we use only single core for handling all data. Yes?
So my question is, do you know any effort to have something like ISIL on ARM processor, because you have utilized ARM processor on your own SmartNIC, if I'm understanding correctly? Yeah, because ISIL is very powerful, but we are concerned about the performance of ARM processor, especially for adding complex features.
I'm sorry. So you're saying, yeah, we're running the SPDK inside the SmartNIC on ARM processor?
Yeah. So for example, so ISIL has good performance for encryption or something like mass computation, but ARM processor may not be so powerful than
ISIL?
ARM processor is not so powerful than Xeon processor, so enough to get ARM processor is enough to offload some storage features on SoC.
So in case of NVMe Fabric Target offload, we don't use ARM processor. So it's done in a special hardware model. So it's powerful enough to, so as we demonstrated, it's powerful enough to get full bandwidth of 100 gigabit of load, all data coming through 100 gigabit port, at least.
Yeah, but even when we do run SPDK on the ARM cores without using this latest feature of offloading, we still see about 3 million IOPS being able to be served by these 16 cores of the SoC.
Yeah, I think what Shuhei was asking about, are you guys familiar with ISA-L?
ISAL, okay,
ISAL,
yeah.
So I think he was asking about.
Yeah, so this does not exist in ARM, of course. So you cannot use it, and if you try to use features that are done with ISAL, you won't get any good performance. But we do try to compensate on that with our offloads that come from the NIC. For instance, in the next revision of the ConnectX family, we're going to have crypto capability inside the NIC in line with the network. So we don't have ISAL in ARM, but we will have encryption, decryption part of the network transport. Yeah.
I have a similar question. I think everybody has the same question, which is that I've used the NVMe Fabric with RDMA, but without the offload. And it was very, very good performance and pretty low latency. But the question is, how does the latency of chaining things sequentially through the SmartNIC, multiple cores, how does that compare with, let's say, a single chip switch, okay, which also adds some latency in experiments that I've done.
So you're referring to the NVMe Snap, the emulation kind of. So it will always be better if you could run the NVMe over Fabric protocol directly from the host. If you have this option, it will be faster because you're accessing the hardware, the network directly and shooting the IOs from there. Obviously, if you have to stop by the SmartNIC, processing software on ARM, and continue from there, you're getting some latency penalty. But this gives you the ability to run plain NVMe on top at the host side. So we see something about, I showed in the slides, between 10 microseconds and 20 microseconds. Depends if you need to go all the way outside the network or if you stay local. That's the penalty of using it. So it's pros and cons. You should decide.
So can I ask a question on this?
Where are you?
Okay, so I have one question here. So I have one question on the NVMe emulation model. How flexible software can emulate the device, right? So let's say, use a very simple example. I mean, if you get register write from the host, from PCIe is a TLP, right? It's a TLP over PCIe. So once it comes into your device, what does the software module say? Like, does it say the TLP, or does it say something you already translated in something?
So with the registers part, okay, I saw 3 parts, right? You have to deal with registers, you have to deal with admin commands, and you have to deal with IO command. For the registers part, it's not possible to delay the TLPs until software answers. So what we do is a trick. We actually acknowledge the TLP immediately in our hardware, and later on we signal the software that there are changes in the register. So asynchronously, software can fetch the registers and see what happened. Luckily, with NVMe, this is all you need, because NVMe spec does not imply any side operations that happen because of reads, for instance, from registers. Okay, so you can safely give back the value that you had saved in the registers.
So how about controller enabled bit? Because in the NVMe, right, you have a controller enabled bit.
Enable bit.
Yeah,
yes.
when the NVMe driver writes it, you need to notify the backend emulation, right? So you have a special handling for some, specific register.
So as I said, the host will set the bit, the enable bit to 1.
Right.
The hardware will send through this vendor-specific channel, will send an event saying, go look at the registers, they have changed. Software will read the registers, will look and see that the enable bit is set to 1, and will read the other registers, will see the admin queue location, the size of it, everything, and will ask to set the ready bit. And since the host is now polling on the ready bit, soonly after it will see that it's ready and continue from there.
Okay, thank you. Thanks, man.
Other questions?
So you mentioned a 10 microsecond additional latency, right? Use
Yeah.
this model. Do you mean this 10 mic is the emulation driver delay, or is it, some other?
So I showed two numbers. One is an experiment where you get the requests from the host through the emulated device into the SmartNIC,
Right.
serviced by SPDK and terminated there, not
Right.
even going out the wire.
Yes.
Okay, so this round trip is 10 microseconds. If you also go to the wire, that's 20 microseconds, not including whatever the disk will take on the other side.
Yeah, so basically your 10 mic includes the local drive access, not just the emulation driver. You include additional components from SPDK, right? That's
Yes, there is some software processing there, of
Okay,
course.
makes sense. Thank you.
Yeah. Yeah. All
Other
right.
questions? Anyone?
Okay. So you can meet us outside in the breaks by the demo booth, and we'll be happy to answer more questions if you have.
Awesome, thank you.
Thank you.